Ken was going to do some sky notes for the moon after tea break, but he's not well this evening, so he's not here. So I think Phil's got a short thing he wanted to show us.
Yeah, it's very short.
If we do that after Indranil's talk, then we can put our feet up and have a so I'm very pleased to be able to welcome Indranil back, because you were here, it was a few years ago now actually, and he tells me he's been in MOND working over the pandemic as well, which I'm a bit of a dent on it, but nevertheless. But it's great to see you again from the University of St Andrews. And tonight your talk is going beyond Einstein to solve the crisis in cosmology. So fairly substantial. So you're going to tell us something of an alternative to using sort of dark matter as to explain much of the otherwise very difficult to explain observations in the universe. So we welcome you back and look forward to hearing your excellent assessment for us. That's great. Thank you.
So I'm going to be talking about an alternative to the standard cosmological model, and this is called Milgromian dynamics, or MOND. Up here I've shown like two important lines of evidence. One of these is in favor of MOND, and one of them not so much. But in any case, we'll have to explain sort of all the observations in a consistent framework, and that's what I'm going to try and present in this talk. So this one is related to the rotation curves of galaxies, which seem to work very well in MOND, and this one to the polar cluster, which is thought to not work so well. So I'll explain what these show later on during the talk. I also want to mention that I did a detailed 150-page review on MOND recently, so I'll show some of the important summary tables from that later on, towards the end of the talk. Right, so the what we're dealing with on the scales of galaxies is a major problem. This is related to the rotation speed of the galaxy, how quickly it rotates as a function of distance. And that's what's plotted here, the rotation speed against the distance. The data points sort of line up there, and what you can tell is that the rotation curve, as it's called, is flat in the outskirts. But if you apply the same sort of inverse square law of Newtonian gravity that works very well in the solar system, then the galaxy would be expected to have a rotation curve which looks like this. And the reason is that most of the mass is within this region, basically. So, just like in the solar system, the more distant planets orbit the sun slower. So it should be the same for the galaxy, that as you go further and further out, the stars and gas orbits the galactic center slower. But that's not true, either in our galaxy or in many hundreds of other galaxies that people have seen. The rotation curves are flat in the outskirts. So this is one of the more major mysteries in astrophysics. I mean, the universe has many mysteries, but this is one of the most striking ones because we're not talking about anything very far away. This is, to give an idea, the rotation curve of this galaxy is kind of similar to that of our own one. And we're about 8 kiloparsec, or about 25,000 light years from the center. And there is, in fact, a significant discrepancy in the rotation speed of the sun around the galactic center. And what you would predict, how fast you would predict it to go around the galactic center using the Newtonian theory. So this particular astrophysical mystery is kind of like right here. It's not about anything very distant. Though, of course, one has to explain some important observations of the distant universe as well, which I'll come on to, and they're related, but this is a really serious and very nearby mystery. One possible explanation for this discrepancy is that galaxies have a huge halo of invisible mass around them, which is the distribution of that has to be tuned to match the rotation curve. So I'll explain later on why this is not a good idea. But just to show you what this dark matter hypothesis would kind of do, basically galaxies would look like this in the dark matter picture. But what you have to understand is that this is an artist's impression. This is the actual galaxy. This blue thing is an artist's impression. There is no direct evidence for it. Actually, galaxies look like this. And what you see is that it rotates a bit faster than you'd expect. That may be because of invisible mass up here, but obviously you can't see it, so that's just a hypothesis. So this is what I was showing on the first slide. What it actually does is it plots this rotation curve results in a slightly different way. So this just plots the rotation speed against the distance, and that's the observations. This is basically the Newtonian prediction. In this case, the discrepancy is much more severe than for the Milky Way. Some galaxies rotate perhaps 10 times faster than you would predict they should rotate at. On the right, though, we've plotted the results in a slightly different way. We've plotted the observed acceleration, which is the v squared over r, the acceleration needed to maintain the stars on their orbits, against the Newtonian gravity from the baryons, or from the visible mass of the galaxy. And of course, the point is that the observed acceleration is a lot more than what you expect. That's shown on this panel by plotting this line of equality. The data is a long way above it. So this line of equality corresponds to this curve, if you like. The important thing about this right panel, though, is that it doesn't just show one galaxy. It shows pretty much all the disk galaxies for which we have observations. So it's 2,700 odd data points from 153 galaxies. And the results follow a very tight relation with a small amount of scatter, but this can be explained purely by observational errors. There is apparently a single universal relation between the gravity and the Newtonian prediction for the gravity. The other thing I wanted to mention briefly is that the values that you have for the Newtonian gravity are very low here. So the solar system would be way off over there somewhere, at maybe 10 to the minus 4, 10 to the minus 3 meters per second square. This data is covering maybe 10 to the minus 9, 10 to the minus 10. That's kind of where the departure sets in. And here, well, we don't have any direct experiments to tell us how gravity actually works at such low accelerations. So that brings me, well, I'll come on to like the MOND hypothesis in a sec. But before I do that, I just want to explain, this is for the disk galaxies, or spiral galaxies as the term's called. We also have results for elliptical galaxies, which look very similar. So this is only apparent relatively recently. In fact, this one actually since my last talk. So what you can see here is, so just to explain briefly how we get the acceleration in elliptical galaxies. The main problem is that it's hard to know how eccentric the orbits of the stars are. So how much is random motions and how much is like ordered rotation. And both of these support the elliptical against gravity. But if it's random motion, then it will kind of not matter which direction you observe it from, whereas if it's ordered rotation it will. And therefore this makes it very hard to infer reliably how much gravity there actually is. That's technically called the mass anisotropy degeneracy. There's basically two ways to break it. Either the material you're looking at is definitely on a perfectly circular orbit, or it's definitely completely random motion. There's no order, circular motion at all. If you could be sure that either of these things is correct, then you could reliably measure the radial gravity. And what's shown on these two panels is basically applying these two methods. It's no good applying the method to a star where you've no idea what proportion of the motion is random or circular motion. So how do we do it? In this case, it's from a halo of hot gas around the galaxy, which is roughly similar to how it works in the sun, basically. Just some hot gas and pressure support holding it up against gravity. Here you can see that the data followed this radial acceleration relation, or RAR, from spirals very nicely. So spiral data is shown in the background in blue. The new data is these colored dots. The color indicates which galaxy it came from. So that's from the X-ray like halos around the galaxy, but you can also do it with this method. What this shows is ellipticals sometimes have a small amount of gas, and because of collision between gas molecules, the gas must be on essentially perfectly circular orbit around the galactic center. Any random motions would cause collisions between gas, which would cause excess energy to dissipate. And the gas would be on a nice circular orbit. This doesn't work in every elliptical, but it works in many cases. This shows data from like neutral hydrogen observations. Actually, in principle, it's very similar to how we do it for spirals. But in spirals, this works most of the time, whereas in ellipticals, it works only a small fraction of the time, because generally they don't have much gas. Still, in the cases where we can apply this, they seem to follow the spiral galaxy relation very well. In this case, the spiral data is shown in the background, the new data, these sort of colored dots. So basically, elliptical galaxies seem to follow the same radial acceleration relation as the spiral galaxies, which is an important constraint that has recently become clear. So this brings me on to the idea of MOND, which basically says that what you were seeing was not a coincidence. I mean, I guess that might seem not too unusual, but that's basically what the MOND theory does. Now, importantly, this was proposed 40 years ago, when a lot of this data wasn't available, in fact, almost all of it. And what it did is said that galaxies don't have dark matter halos around them. Instead, we need to modify the Newtonian gravity, which by this point was almost 300 years old. What you need to do instead is say that gravity from a point mass follows the usual Newtonian inverse square law only when the gravity is stronger than some threshold, A0. Beyond that, it follows an inverse distance law. Basically, if it did, then it would be possible to equate this inverse distance law with the centripetal acceleration v squared by r to get a flat rotation curve. But exactly why it's constructed this way, I'll come on to in a sec. The important thing is that each mass then, or each galaxy, defines a MOND radius, beyond which you need to follow this law instead of the usual gm over r squared law. Then, of course, you need to know what the value of A0 is. Importantly, this value of A0 can be determined from only a small number of rotation curves. So it's sort of fit to the data empirically. This was fixed before I was born. This MOND then has to fit everything else discovered subsequently with the same value for A0, if it's correct. Now, one obvious consequence of this, if you equate that with the centripetal acceleration v squared by r, is that v squared will equal square root of gm A0. So the rotation curve of any galaxy will flatten out at a level given by the fourth root of gm A0. So I've included a b subscript to specify that this is just the visible mass. In MOND, galaxies should not have any invisible mass. Now, one thing that can be done is to test this prediction So I'll show that on the next. Well, okay, I'll show that now and come back to that. If you try to test that by plotting the flat line level of each galaxy's rotation curve against, which is on the x-axis, against its baryonic mass, or visible mass on the y-axis, you'll notice that the galaxies kind of fall on this dotted line, which is the MOND prediction. Now, the important thing to understand, so obviously that's quite consistent with the MOND prediction. Right? Now, one important thing to understand is like how would any of this make sense if gravity was actually Newtonian? To be honest, the answer is that it wouldn't. But I'll just explain briefly how people try to make sense of this. They basically, if galaxies had a constant proportion of visible to dark matter, and this was the same as the sort of cosmological proportion that's fit from like early universe observations, then galaxies would follow this line, which is wrong. But anyway, what the astronomers try and do is postulate that galaxies lost a certain, like a very large proportion of their baryons to things like supernova explosions blowing out the gas, for example. And as a result, they would lose a lot of baryonic mass, but they wouldn't really lose much dark matter. As a result, they would still continue spinning at the same speed, because the gravity mostly comes from the dark matter, supposedly anyway. And as a result of that, galaxies would kind of move along this dashed red line, which is supposed to be almost vertical, but a little bit towards the left. And as a result of that, supposedly galaxies would fall somewhere around here. But the main problem with this is that the processes that I'm talking about are very random. In a dwarf galaxy, exactly where the supernova occur, or how many there are, whether there's 5 or 10, for example, will be random. Whether they're near the center or near the edge, and if the galaxy merges with other galaxies, things like this will be random. So galaxies could essentially fall anywhere below this line. That's the reality of what would happen in a lambda CDM universe. So basically a universe governed by the standard cosmological model. Therefore the likelihood of this slope of 3, which is predicted for a constant ratio between visible and dark matter, magically turning into a slope of 4 with 0 scatter is negligible. It's basically impossible. That's the what is called the baryonic Talley-Fisher relation. Let me see if there's anything else on you wanted to present. No, okay, we'll leave that aside. One way to put this, another way you could look at the equations of MOND is that the gravity is related to the square root of the Newtonian gravity in the weak field regime, when the gravity is very weak. But when the gravity is very strong, you just recover the Newtonian gravity again. So like in the solar system. Now this is for like a spherically symmetric problem. If you have like more complicated geometries, such as like 2 comparable masses or 2 interacting galaxies or something, then basically you need to use this field equation, that will reduce to just G equals Gn multiplied by some function nu, which is the interpolating function in MOND. So yeah, that's basically how we solve like more complicated geometries by solving this on a computer usually. Right, so that's the basics of the MOND. Now, one thing, in the non-relativistic case at least, so when the motions are much slower than the speed of light, relativistic MOND theories have also been developed. I think the first sort of reasonably well-functioning one was put forward in 2004. So a lot of progress has been made since then. Recently, there was a nasty shock to a lot of the MOND community when people realized that gravitational waves travel at the speed of light, which is not really that easily understood in MOND, but it was within a few years quite possible to set up a relativistic MOND theory where gravitational waves travel at the speed of light. So the theory was adjusted to accommodate this with minimal effort, I think, relatively minimal effort. Then one thing that usually happens in these theories is that the relation between the gravity felt by sort of non-relativistic particles, slow-moving particles, and the angle by which a ray of light going through the system would be deflected. The relation is the same as in general relativity. What is different is that obviously in MOND the gravity is itself like much stronger than in the Newtonian case. But otherwise the relation between the deflection angle and the gravitational field is the same as in general relativity. So one thing that has recently become possible is to test this sort of prediction using weak lensing by galaxies. So this is when galaxies slightly distort the shapes of background galaxies, like gravitationally. And if you plot the weak lensing data on an acceleration diagram, so you plot the observed acceleration against the acceleration, the Newtonian gravity from the visible mass, well, the line of equality is here. The spiral galaxy data is shown in like blue shading in the background, and the red points show the spiral data. The new data from weak lensing measurements of galaxies, so you have to stack many thousands of galaxies to be able to see the signal properly, but the data basically follow, they come around here, so they follow actually the extension of the spiral galaxy relation. They follow a very tight radial acceleration relation, essentially. The important thing about this is that basically MOND works down to an acceleration 100,000 times weaker than A0, which is up here. Well, 100,000 times weaker in this in the Newtonian gravity. The actual gravity is, of course, like weaker than A0 by the square root of that, because that's how the MOND works. So we've got 5 orders of magnitude here, and that corresponds to 2.5 on the y-axis. Yeah, so the weak lensing by galaxies also works, and essentially this means that MOND works down to an acceleration 100,000 times weaker than A0, which is not as far as you can really go with the data at the moment anyway. You'd basically start probably seeing impacts of other galaxies if you went out much further from a galaxy. Then what I wanted to explain is obviously this kind of thing is not very easy to explain with Newtonian gravity and dark matter, but to show like one problem with the idea, I'm going to show like a rotation curve fit to a galaxy in MOND and in the Newtonian gravity plus dark matter. So the in each panel, like the best fitting theoretical model is a solid line, and the data is in, well, with the points in error bars. Now what you can see is that Newtonian gravity plus dark matter managed to fit the data pretty well. Admittedly, the vast majority of the gravitational force needs to come from the dark matter. So this is the dark matter curve, almost the same as the actual one. That's because the gravity is a lot more than the baryons can possibly provide in the Newtonian picture. Now you might be wondering, well, hang on, but in the MOND case, it's not possible to fit the data. So that's not so good for MOND, right? And the answer is it's actually not very good for MOND if the data actually existed. Unfortunately, it doesn't, because what the astronomers doing the fit were given was a rotation curve of one galaxy and a photo of a different one, just to see like how honest they were being, basically. Like, could they still fit the fake data? And the answer is apparently you can with the Newtonian model. The answer, and the reason for this is quite simple. if you put in an arbitrary amount of invisible mass, you can fit almost anything. So that wasn't necessarily very surprising, but it still illustrated an important issue, which is that this picture doesn't predict anything. It only sort of explains the facts afterwards. One important thing that has become clear recently, so I should explain, it's quite difficult to falsify such a theory as well. Obviously that's what I'm working on, but it's very difficult. One thing that would happen though in the dark matter picture is that galaxies often develop like a bar in the central region, so like a rod-shaped structure, if you look at them kind of face on. And this is kind of spinning around, like the galaxy basically. But the rate at which it spins should be slowed down by friction against the dark matter halo. And this is not like an electromagnetic friction, this is like a purely gravitational effect. Basically the bar will concentrate dark matter particles behind it. There'll be like a dark bar which is like trailing the visible one, if you like. And that would slow the bar down. Assuming the dark halo even exists. In that hypothesis, the bar would slow down. If there wasn't a dominant dark matter halo around the galaxy, the bar pattern speed would remain constant. So that's kind of what's shown in these simulations. The important thing to look at are the red and the black curves. The red curve shows like a standard simulation with neutron gravity and dark matter. You can see the pattern speed slows down substantially over like 6 billion years. It's still much less than the age of the universe. In the MOND model, the pattern speed remains more or less constant. So this allows for an important test of the two theories, which I'll show the results in the next slide. What I want to explain briefly is that omega p can't by itself directly be used to test the theories because it depends on various other parameters of the galaxy, how big it is and how massive it is. So instead, observers they quantify if the bar is slow or fast using the R parameter, which is the ratio of the co-rotation radius of the bar and the bar length. The co-rotation radius is basically the radius where the angular frequency of the bar matches the angular frequency of a star orbiting the galactic center. So the star and the bar both have the same rotation period. What happens because the rotation curve usually rises almost linearly in the inner part, basically if the pattern speed falls a little bit, that raises the co-rotation radius quite a lot. Therefore the R parameter goes up quite a lot. So in other words, like a slow bar corresponds to high R and fast bars correspond to R 1 to 1.4. There's various reasons why R couldn't really be less than 1. It's not really a stable configuration. So this is the important thing to look at, like what values of R do real galaxies have, and also in the simulations. But basically trying to extract this from the simulation, from the observation, is a much more robust way to do the comparison than the pattern speed. So this is what I've shown on here for the standard cosmology simulation. So the standard cosmological model is called lambda CDM, and the CDM is the key bit for us. There's the cold dark matter halos around galaxies. What happened here, the observations are shown in black. So basically, most of the probability lies in this 1 sigma region. What's shown here is the mean value of the R parameter across the galaxy population, and how much it varies between galaxies, the dispersion. That's not super important. So it's merely the x-axis which is important for us. Now in the standard cosmology simulations in lambda CDM, the latest sort of highest resolution one is the TNG 50, which came up here, but the results were similar to the TNG 100, which is a larger box, but slightly lower resolution. The Eagle 100 is slightly older. So it's simply not as good as either of these two by most standards. But still, the results are very similar. Basically, our parameters mean value must be around here in the simulations. But it's actually here observationally. This leads to a catastrophic failure of the Lambda-CDM model. In the TNG50 case, the tension is 13 standard deviations. The level of tension differs slightly between the simulations, right? But the main reason is that the number of galaxies in the simulation that was suitable for the analysis differed. So you can see that when you have more galaxies, slightly more, and when you have less galaxies, slightly less. The simulations are internally consistent with each other, but they obviously disagree from the observations in a major way. So unfortunately, this paradigm is completely wrong. It's just how it is. Right. So if I try to show like how this works in the MOND case, first of all, I've shown the TNG50 result again there. And the observations again I've shown in blue this time. In MOND, we basically did simulations of, well, we did simulations of like 5 galaxies, but these 3 were most suitable for analyzing the bar. I think the other 2 had too few particles to easily analyze. And we chose the sizes and gas fractions to be realistic based on like what's the typical size of the galaxy with the stellar mass, so how much gas does it typically have. So choosing all that sort of in a realistic manner and analyzing the simulated galaxies using basically similar techniques to how observers would analyze real galaxies. So there's a subtlety here, which is that in a simulation you could theoretically look at a video to see how quickly the galaxy is spinning. You can't do that with a real galaxy, but there is a special trick which can be applied in real galaxies. And we did that in the simulations as well. What's called the Tremaine-Weinberg method. What happened, if you do that, basically we consider snapshots of the simulation at different times as representing different galaxies, just to get the statistics. The MOND simulations, they ran for 5 giga-year. The end result is around here for the first, well, for like 1.5 to 5 giga-year. If you look at the like latter half of the simulation after 3 giga-year, it ends up here. So basically similar. So this is actually very similar to the observed value. One thing that is not quite right in the simulation is that they have far too little scatter, but that's because we only have a small number of galaxies with like, for example, I think each stellar mass is only one size of galaxy. Like if you consider the whole galaxy population, there will probably be a lot more scatter. So these would move up. Basically this is almost consistent with the observations. MOND seems to have no trouble explaining why galaxies have fast bars. Now the reason for that is fairly obvious. It's because bars in MOND do not slow down. The reason they do not slow down is because there is no halo around the galaxy to slow the bar down. There's some material in the disk, but there's not very much. And the more sort of angular momentum it absorbs from the bar, the further out it goes. It gets pushed out, and that weakens the coupling further. So basically, bars cannot really be slowed down much in MOND. They sometimes oscillate in the pattern speed a little bit, but they don't really systematically slow down. So galaxy bars apparently can be explained pretty well in MOND. It looks like it anyway. People haven't done a cosmological simulation similar to TNG50, but this should work out. Whereas in the standard cosmology, it doesn't. So now I've explained about like how galaxies work. Now I want to come on to the cosmological aspects of MOND. What I wanted to say is I'll explain later on why we need to do things this way in MOND, but it's the most natural way to do it. So in a cosmological MOND framework, one thing that has become clear over the years is that you would still need some additional component of mass in addition to the visible mass, like the cold dark matter in the Lambda-CDM model, but instead of being cold, it would be hot. What I mean by that is that it would not form halos around galaxies. but it would still exist on larger scales. It would be a very diffuse component of matter. I'll come on to explain later why we think this is a good idea. But basically this is supposed to be most likely sterile neutrinos, which are hypothetical fourth type of neutrino with a rest energy of 11 electron volts, so a little bit more than for the ordinary neutrinos, about 100 times more. Then the overall cosmic pie chart regarding what the universe contains would look much the same as in the standard cosmology, except the cold dark matter component will be replaced by hot dark matter, which would lead to the lack of massive dark matter halos around galaxies. But there would still be dark matter on larger scales, which is going to be important in this set. There's a few things that would happen in this cosmology which are much the same as in the standard model, allowing us to preserve some of its successes. So it does get some things right. For example, the abundances of light elements, so the fact that the universe converted like a quarter of the hydrogen into helium in the first few minutes would be more or less the same in this model. It would be like a percent level difference, so it would be very hard to notice. The main difference is that MOND is applied only to the deviations of the density from the cosmic mean when you're doing the equations, there's a special nonlinear effect that arises in MOND called the external field effect, which I don't want to touch on too much. It's not super important for this talk. So what I wanted to explain is the cosmic microwave background is often considered like a problem for MOND, but it's actually not. The main reason is that the cosmic background radiation was emitted when the universe was about 1,000th of its present size, so only about 400,000 years after the Big Bang. And at that epoch, the typical gravitational fields were much stronger than A0. So the universe was much more homogeneous then than it is today, but it was also much smaller, and that's why the gravitational fields were actually like stronger than today typically. Like the gravitational fields between galaxies are much weaker than that nowadays. That's because they're much further apart. First of all, MOND doesn't really affect the physics of the universe prior to this recombination, or the emission of the CMB rather. Because the expansion history of the universe would look much the same as in lambda CDM, the CMB would be at the same sort of distance to us. The other thing that's important is you might be wondering, but even if the gravity is basically the same as Newtonian, replacing the cold dark matter by hot dark matter, would that affect the CMB? And the answer is it would have only a very negligible impact. For example, you can see what the Planck collaboration wrote in their paper, that if the sterile neutrinos have a mass, but they only consider masses less than 10 eV, because if the mass was higher, the particles would be so massive that their effect on the CMB anisotropies is identical to cold dark matter. In other words, in the lambda CDM picture, people are used to thinking of the particles that make up the cold dark matter as being very massive, as having masses of many billions of electron volts. But all we can actually say from the CMB is that the mass must be more than 10 electron volts. Anything more than that would actually fit the data. That is why we were using a mass of 11 in MOND, but also because if you use a mass of 11, then the abundance of the sterile neutrinos, the density, the energy or the mass density would be the same as for the cold dark matter in the standard model. This is in fact what is shown here. The observations are shown there in terms of the smaller angular scales are shown here, large angular scales over here, and this is the amount of power you have on that scale. Now, how much the cosmic microwave background differs from one region of sky to another on that scale. So basically on 180 degrees over L angular scale. So there's these acoustic oscillations that you might be familiar with. That can be explained in lambda CDM, of course. Well, that's shown as the red curve. But the blue curve also fits, and that's like the MOND fit. So it's actually possible to fit the observations very well in MOND of the CMB. Another interesting thing is that the parameters in the MOND fit are slightly different. You actually have a slightly higher Hubble constant, which actually is perhaps a helpful feature in light of the Hubble tension. So this wouldn't solve the Hubble tension by itself. So yeah, you can fit the cosmic background anisotropies pretty well in MOND. Now you might be wondering, okay, but if MOND wasn't important at that epoch, when does it become important? And the answer is it becomes important only when the universe is 50 times smaller than today, or at later epochs than that. So basically the first 50 million years of the universe, MOND isn't very important. But after that it is. In fact, basically the typical gravitational field drops off with the size of the universe. So when the universe becomes 1,000 times bigger, the typical gravitational fields are about 2% of A0. So MOND would be very important at the present epoch, for sure. Now, that's the cosmic background radiation. The other thing I was showing you at the start is on the right side is the bullet cluster, which is also argued to be like horrifically bad for MOND. And the reality is that it's not ideal for MOND, but it can be explained. The way one would do that, so first of all, what's shown here is the X-ray peaks, so where you see the brightest like X-ray emission from the bullet cluster. So where the two galaxy clusters have collided with each other, right? So that's where the X-rays are mainly coming from. Now, for the important breakthrough in the bullet cluster was that if you try to look at the distortions to the shapes of background galaxies, you look at the weak lensing, and you try to infer where the gravity is coming from. The gravity apparently is mostly coming from here and here. These points are offset from where the X-rays are. So the standard explanation is that the two galaxy clusters have like gas, but also a dark matter halo. As they hit each other, the gas got slowed down by gas friction, hydrodynamical effects, and the dark matter just kind of plowed through almost unimpeded. I mean, they both experience gravity, but clearly the gas had more forces decelerating it than the dark matter. As a result, the dark matter kind of got ahead of the baryons, the gas. So that's the standard explanation. Now, there is no way to avoid a similar explanation in the MOND context as well. In the MOND context, though, one thing to understand is that we can fit the observations very well if you have a particle more massive than 2 electron volts of the c-square. Basically anything above that would be able to fit the bullet cluster. Now the reason why you can't have arbitrarily low particle masses is because there's a limit to how many sterile neutrinos you can pack into a certain region of space. Because we can see how much mass there is, that imposes like a lower limit on how much mass each particle must have. They have to be sufficiently massive. So the limit to the number density of the sterile neutrino is basically the same principle that keeps you from falling through the chair you're sitting on now. So it's the same kind of physics, but this is what the bullet cluster actually tells you. So when people look at a bullet cluster, they think like, well, that must indicate there's dark matter. That logic can't really be disputed in MOND, but the dark matter particles don't need to be very heavy. They just need to have a mass more than 2 electron volts. So of course, if you had 11 electron volts it would be fine. You would need much fewer particles than the maximum you're allowed to pack into this region. The other thing is that there's many other galaxy clusters where the gravity towards the center of the cluster is much more than you predict in MOND if you just had the visible mass. But if you were to add sterile neutrinos, then this would work. if you added sterile neutrinos with this mass, which I was showing just now fits this cosmic background radiation pretty well, what would actually happen is the required number density of the sterile neutrinos would rise towards the center of the cluster, and it would kind of flatten out at the center at the maximum allowed value. And this coincidence happens in like 30 different clusters which were analyzed in this paper. So it's a nice kind of coincidence. Yeah, like I was saying, the CMB only tells you that the mass is more than 10. So basically, with a mass of 11 electron volts over c squared, you can fit the cosmic background and the galaxy clusters pretty well. The other thing I didn't mention is that the ratio between the total mass of a galaxy cluster in MOND and the visible mass of the baryons is more or less the same in the most passive clusters as this cosmic pie chart, which is inferred from the cosmic background radiation. So this kind of tells you that there needs to be basically 5 times as much dark matter or sterile neutrinos as the baryons. But this is based on the cosmic background radiation. You can infer the same proportion though from nearby galaxy clusters. So this is a strong piece of evidence that the universe really does have something in addition to the visible mass. Even in a MOND gravitational framework. That doesn't affect clusters much, by the way, because typically the accelerations are above A0. So MOND, the gravity law in MOND doesn't really do much for you in this case. So that's the bullet cluster, which we do need to explain, of course, in MOND somehow. One thing that I worked on during my time in MOND, so I helped Anna supervisor on a project which was related to the formation of structure. So she provided a couple of slides which I'll show you briefly. Basically, if the standard cosmology is correct, you should be able to predict when different structures form, when the first galaxies form, when galaxy clusters form. You might have heard that there are serious problems with these predictions. That's what I'll come on to in a sec. But basically, you should be able to predict, at a certain epoch, what kind of galaxy clusters you could have. And if you see anything that's too massive, then it couldn't have formed in that cosmological paradigm. Because you can see the initial density fluctuations here, basically. So we analyzed a galaxy cluster known as El Gordo, which is a collision roughly like a bullet cluster, but it's much further back in the past. So the universe is about half its current age then, whereas the bullet cluster is much closer to us, much more recent. Then there's what happened, 2 clusters interacted or collided with a total mass of 3 quadrillion solar masses. This is very massive, by the way. They fell into each other with an infall velocity about 2,500 kilometers a second. This is actually not good because it's higher than the Newtonian escape velocity. You'll see in a minute that this causes problems. Basically, it's the most sort of brightest galaxy cluster at that redshift in multiple different ways of looking at it. There's a main cluster and 2 faint tails. Now, to analyze whether this is actually consistent with the standard cosmology, we considered hydrodynamical simulations that can fit the detailed observations of the cluster, but they have to assume 2 clusters of particular masses and mass ratio fell into each other. This is sort of a few 100 million years before the merger, the interaction typically. And then you have to check though if such massive clusters could plausibly have formed in a large cosmological simulation, which kind of goes from the very, very early universe up to well, it has to go up to at least 7 billion years after the Big Bang for this to work. But most simulations go all the way up to the present epoch, of course. We, on the hydrodynamical simulation side, we use this paper. On the cosmological simulation side, we use this one, which has a very high well, box size of about 6 billion parsec, or almost 20 billion light years on a side, because we knew we were dealing with something which was not very likely to happen in the standard cosmology. What I've tried to show in this graph is the mass redshift distribution of galaxy cluster collisions, of pairs of galaxy clusters, which are headed towards each other, well, they might not collide, but as long as their velocity is at least vaguely headed towards each other, we've included them on this plot. And what we've shown is the mass in logarithmic units, and the scale factor of the universe. How big was it compared to the present size? So L border is when that occurred when the universe was half its present size. This shows all the clusters, but what it shows is like the sort of number density of clusters per pixel, if you like. And basically most of the cluster collisions should be in this region of parameter space. So basically if you saw a galaxy cluster collision with this kind of mass, when the universe was like 3/4 of its current size, that would be the kind of thing you typically see. At 1 sigma, everything you see in the past light cone, so in the surveyed region of the sky, should be within this region. At 3 sigma, it should be within this region. And at 5 sigma, it should be below this black line. L border is significantly above that. It's up here. We've allowed like reasonable uncertainty on the mass. But the redshift is very precisely known, so I haven't really shown any uncertainty on that. What you can see is that basically you'd have to draw, well, the contour going through that red cross is this solid red line. You can ignore the dashed red line, but this solid red line, well, it's a very significant outlier. The way we quantify it is we work out the total probability like outside that red line, essentially. That's how the probabilities are quantified. And what that, because like even if you had the right cosmological model, you would never sort of exactly match the probabilities of L border, right? So what you do is you draw a contour through it and you work out the probability outside that contour, or in other words, the probability in regions of parameter space where the probability density is lower, to be more precise. But that's in this plot outside. The probability of L border, or more precisely, the probability of something as bad as L border for the standard cosmology, or even worse, is 7.5 times 10 to the minus 10, which corresponds to a 6.2 sigma outlier. What that means is the likelihood of the standard model being correct and being able to explain the existence of even one object like L border in the surveyed region, given that it sits here, is below 1 in a billion. There's a few other cases like this which we didn't analyze, but just this object alone falsifies lambda CDM cosmology at very high significance. We argued in the paper that based on previous simulations done in MOND, this is actually not that unusual in the MOND cosmology. In fact, in the surveyed region, we estimated that there should have been, on average, 1.2 analogs to L border, which is basically correct. So that's something we mentioned in there. But in the standard cosmology, it absolutely won't work. And also, I should explain that recently there have been studies of galaxies, individual galaxies which exist with such high mass and such high redshift, thanks to the James Webb telescope, that these also contradict the standard cosmology. But whether they're consistent with MOND is less clear for the time being. Great. What? Oh yeah, the clock stopped on this as well. Yeah, let me take control.
And goes the technology.
Yeah, try escaping.
God, watch that pair of seats.
Oh, there we go.
Yeah, I think Well, it went a few steps ahead. That's not too bad. Let me see if I can get back now, though.
Yeah, working memory. Strange.
Yeah, I think it just overheated a little bit.
Maybe. Working memory.
It is quite warm in here.
Let me try to get this back to where I was trying. Ah.
So this mouse, I'll take the mouse out.
Okay.
I've got a torch. I've got a tape measure.
Maybe I should use it to cover this one because I don't like the button. But, right, let me try playing it again. Shift F5.
Like being at school with a video recorder, isn't it?
Just a sec while it connects up. Alright, let me try playing this then.
Yeah, that seems to be changing now. Oh, it's gone off again.
What's it doing?
I think it was just doing what you asked it, but delayed.
Oh, it's like catching up.
Yeah, I think it understood now.
Yeah, probably if you point it towards the laptop rather than the screen.
Yeah, I might make it. Alright. That's actually wasn't a bad place for it to frozen. What I was wanted to explain the last part of the talk briefly is that I did a review recently on MOND. So I was invited to do this review, which ended up being almost 150 pages in symmetry. So I'll explain some of the main sort of things we found in it. Obviously, it didn't really involve any new research, but it summarized the existing one in a novel sort of way. So the main thing we did, in addition to sort of citing the relevant works and so on, is try to test the standard cosmology of lambda CDM and MOND against observations. But the way we do that is using a special 2D classification system. What goes on the different columns, x-axis if you like, is the level of theoretical flexibility that the model has in matching certain observations. So like how much can it be tuned to match that, or is it something that really kind of follows directly from the basic assumption of the model? And on the y-axis is like the usual thing of like how well does the theory actually fit that observation, or observations of that class of astronomical system usually. So is the agreement excellent, or like it strongly disagrees? So the thing to understand is that ideally there would be a clear a priori prediction about certain astrophysical phenomena, not informed by the data in question, and obviously ideally it would sort of agree with the observations when they eventually prevail. That means that ideally things would fall in this cell, but in general, if they're like towards the top left, that's good for the theory. What happens if you have an unphysical theory? So for example, when people thought that the Earth was at the center of the universe and the planets went around it, they were able to add a large number of epicycles to the motions of the planets, and this actually fit the data somewhat well. But it also introduced a lot of flexibility, which is perhaps how people could, and perhaps how they did realize that it wasn't such a great idea. The way to look at the table then is that basically theories which are on this diagonal, they have the same amount of theoretical flexibility as the level of agreement with observations. In other words, like if they dare to make a very strong prediction, it's completely wrong. But if they have a great deal of flexibility, then it sort of unsurprisingly, matches the data really well. Now, even a wrong theory can do that, by the way. I mean, the epicycle theory kind of fits a lot of data, somewhat well. So basically, unphysical theories would be on the diagonal. Good theories would be like above it, towards the top left. So this is the situation for the lambda CDM model. There's a few things towards the top left, but not very many. So one way to look at this, for example, is in these 4 squares, there's only 5 tests, for example. Now, if you try to do the same thing with MOND, it ends up like this. The main difference, so first of all, both in lambda CDM and MOND, they have not the same number of tests. You have about 30 tests in both cases. Largely they're the same tests, but some of them are unique to one, some of them are unique to the other, for various reasons. Some tests can't be directly applied to both theories. But here you notice that in these 4 squares, there's 12 tests. Well, there's 6 here, and there's 6 here. This one, so in both theories, I've colored one test with a hollow dot. That test is not supposed to be counted because the relevant observations were actually used to construct the theory, or to basically to fix the parameters. So usually when people do standard cosmology, they sort of fly by the CMB, if you like, and use the parameters they infer from that as the cosmological parameters in their model. In MOND, they don't use the CMB quite like that, but they use the rotation curves of high surface brightness disk galaxies in that way. So galaxies similar to the Milky Way. Low surface brightness galaxies were not known before I was born, and therefore they were not used in constructing the theory. That's why they can be considered as an independent test. But the high surface brightness galaxies, certainly MOND was designed to fit. So that doesn't count as a successful MOND as such. But yeah, one other important thing to realize, another way to look at this is, first of all, there are many more things towards the top left, but also in the lambda CDM case, there were many serious falsifications of the model, which are detailed more in the paper. I showed some of them today. In MOND, we didn't manage to identify anything. Obviously, this went through the peer review process, but the referee didn't identify anything either. That was in very serious tension with MOND. There are things which are unknown how they would work in MOND, but there's nothing where you know how it works in MOND, and the observations are discrepant with that. So that's how it kind of works in MOND. Then if you try to compare the two theories, what we did is we just subtracted the theoretical flexibility score from the score for how well it agrees with the observations. Because obviously if it agrees with the observations better, that's good for the theory. But if the theory is more flexible, that's not good for the theory. At least if it matches the observations, it will be less impressive. So then what I've done in this table is I've shown like this score, but in this case I've sorted it in increasing size. So these are small scales and these are very large scales. You can see that in most scales the MOND performs significantly better. Even on the megaparsec at larger scales. So these are larger than any individual galaxy. Most of the tests MOND comes out ahead. There's a few where the lambda CDM, I think, comes out ahead. So in particular the Bullard cluster obviously is more in favor of the standard cosmology than MOND. But what I was trying to argue in this table is there's maybe 3 or 4 things like that and 20 things which argue the other way. So that's basically the overall situation. And you can also see that some of the best successes for the lambda CDM are on very, very small scales to do with the gravitational waves and the Big Bang nucleosynthesis. One important thing to understand, these do not have anything to do with lambda CDM. In other words, neither of these assumptions has anything to do with the presence of dark energy in the universe or the presence of cold dark matter. The the fact that gravitational waves should travel at the speed of light is related to the assumption of general relativity, which predicted that they should travel at the speed of light. So the fact that they do is obviously a success. It doesn't falsify MOND, because MOND can also do that. But it's a success story for general relativity. It doesn't really prove that the universe has cold dark matter or dark energy in it. And the Big Bang nucleosynthesis is basically the same. It sends to the very early universe when both these things were unimportant. The universe is mostly radiation. Still, there are some successes of this lambda-CDM picture where it is better than MOND, sometimes, but very rarely. And then this is what is arguing about not counting the open dots. But you can see that that doesn't matter too much because there's many more tests that can be applied. So what I got out of this in the end is that we got an average score of close to 0 for the lambda CDM. It's actually slightly negative because there's some areas where it has a lot of flexibility, but it's still unlikely to match the observations. It doesn't match very well. And in MOND, we got a score of about +2. Now, a score of about 0, as I was arguing before, basically implies you have the same amount of, same level of agreement with observations as the flexibility you put into the model. So essentially, the score is the same as you would have for an unphysical theory. Now, for MOND, a score of +2, obviously it's not perfect. I mean, ideal world would get +4, but what actually happened in the real world is you got +2, which means you either had a clear prior expectation, and when you then got the data to test this, it plausibly agrees with the observations. Or it could mean that you need some auxiliary assumptions, that it's not just MOND, for example, it's some additional physics as well that you need to model, and but it doesn't affect the results very much, as long as it's kind of done plausibly, reasonably well. If you do all that, the result then ends up like absolutely perfectly agreed. So basically +2 corresponds to like scenarios like that. So on these graphs, +2 would correspond to like being here or up here maybe, on average. Yeah, that's right. So that's the overall score. So the conclusion I drew from this in the review is that the lambda CDM model has very little physical content, especially inside individual galaxies. Obviously, it agrees with some observations. Otherwise, people wouldn't widely believe this model. But realistically, this is driven by the ability to put an arbitrary amount of invisible mass wherever the data needs, after you've had a look at the data, not like predicting beforehand, in order to save like the 350-year-old theory of gravity, for reasons that are not completely clear to me. But anyway, that's basically probably what is driving the agreement with observations in the lambda CDM model. Anyway, the conclusions for this talk then is that the cosmological context or beyond individual galaxies usually is thought to be quite problematic for MOND, but actually we can have a viable MOND cosmology called this new HDM, which was proposed about 13 years back. And it can fit the expansion history and the cosmic background isotropies, but the growth of structure would deviate from standard cosmology after about 50 million years. Could fit the galaxy clusters, and the galaxy rotation curves are well known, they do work well in MOND. The additional sterile neutrinos do not really affect galaxy rotation curves, assuming the mass is below 100 eV by c squared. So there's a certain range from 10 to 100 in which you could put the mass, but the optimal value is 11 surely. The other thing is this new HDM cosmology. It explains various failures of the lambda CDM on small scales. So one thing I've explained is it can help with the planes of satellite galaxies around the local group and Centaurus A. I think I mentioned that last time. So I didn't mention that here. but it doesn't really work in the standard cosmology at all. Other things such as the bars I did mention today, and things like the properties of dwarf galaxies in the Fornax cluster also do not work in Lambda-Senior, but they work in the MOND cosmology. On larger scales, there's the KDC void, which is a large underdensity, which can probably explain the Hubble tension. That works all right in MOND, but not in the standard model, and LGOD, which I talked about earlier. So yeah, well, there's these two blog posts. You will keep up to date on like some of the latest developments in MOND by signing up to this mailing list, which is detailed in post 62 on here. So I set that up about a year back. It wasn't actually my idea, I was asked by someone else to do that. Then the last slide I wanted to mention is that we're actually hosting the Global MOND Community Meeting or Conference in St. Andrews, which is a great privilege for me. But everyone in other countries really wanted us to host this in the UK for the first time. So that's the logo we have, and yeah, you can see the rest here. So that's everything I wanted to say. This summarizes most of the different scales, tests of MOND. Thank you for listening.
Thank you.
If there's any comments or questions for Indranil.
Yeah.
Is that
A lot of what you said seems to be dependent on the sterile neutrinos.
Yeah.
Is the source of sterile neutrinos the same as other neutrinos?
The source?
The source, where they come from?
Well, they came from photons, like sort of converting into sterile neutrinos and antineutrinos in the early universe in the same way as the ordinary neutrinos formed. So basically, if there is like a way for a particle, well, if there is like a stable sort of energy state, which is a sterile neutrino, then sometimes photons will convert into that. And that's essentially how we think all mass formed, basically. But the point is, as the universe expanded, the chance of them like colliding with each other again and converting back into a photon would become low because of the expansion of the universe. So you would basically have a certain number density of any particle would be kind of frozen out. Basically the number density you can calculate, but the mass density depends obviously on the mass of each particle. And if the particles at a mass of 11 eV by c squared, then the mass density would be basically the same as the cold dark matter in the standard model, which would allow us to replicate some of its successes. But regarding the sterile neutrinos, there is actually some evidence for it from the terrestrial experiments that they actually exist, which have nothing to do with astrophysics. So I did mention that briefly in the review, that there's some
Something a bit more down to earth. Well,
yes.
metaphorically.
No, literally.
Has there been any analysis done on globular clusters in the galactic halo
Yes.
for testing?
Yes, there was actually. Well, I'll tell you an interesting story about that. Like, there was the outer halo globular cluster NGC 2419 was argued to like not be consistent with MOND, by Rodrigo Mata, and then there was some papers by Bob Sanders who argued that actually if you do the analysis more carefully and allow certain source of uncertainty that are neglected, then it actually works well in MOND, or it can be made to work, okay. Now these rebuttals were sufficiently good that apparently 2 years after all this happened, like 2011-12, Rodrigo Mata is actually one of the strong supporters of MOND now, which despite him writing that it absolutely can't work this 2 years earlier. So it's very hard to like test MOND there because of the different uncertainties, but there's no strong evidence against it from there either. There was a very interesting study, not from the main body of the cluster, but from the tidal tails of Palomar 5, and these were argued to be asymmetric in a way that makes much more sense in MOND. So that's one one of the few signs of evidence from globular clusters actually in favor of MOND.
What is a baryon?
Basically it's a proton or a neutron. So essentially when astronauts talk about baryonic mass, they just mean like ordinary mass.
Stuff we can see.
Yeah, exactly. So because electrons have very little mass in comparison, they tend to be not.
So just on those like earlier diagrams that you had like baryon stuff.
Yes,
I
I.
understand what I was actually looking at.
So the things like on here, where you show the baryonic acceleration, what that means is the. So this isn't labeled ideally. What it means actually is the Newtonian gravity of only the visible mass. That's what's on the x-axis. But in general, when astronauts talk about baryonic mass, they just mean like visible mass.
Okay.
One question I have about the, well, it's kind of like combined two questions. The, what do you call it, boundary between Newtonian and non-Newtonian
Yes.
seems to be a little bit arbitrary. And also, is it a continuum or is there a sudden shift between modes? Or would you expect to see a blending between Newtonian and non-Newtonian?
Yeah, you would expect to see a blending. Now, one thing I should explain, this A0 parameter is somewhat arbitrary. It has to be inferred from observations.
Right.
But one has to understand, like, the same question could be asked about the capital G in the Newtonian theory. That's also arbitrary, but I think that's not necessarily a problem. What you have to do is like fix it using some data, and then not use that data to argue in favor of the theory. One would have to use other data to do that.
I just wondered if there was a theoretical...
Theoretically, there are some coincidences which suggest that A0, well, that gravity should be non-Newtonian at very low accelerations. So basically the energy density of a gravitational field, obviously it's lower the gravitational field strength. If it falls below A0, that's also approximately when the energy density in the gravitational field falls below the dark energy density, which is a quite unusual coincidence. And basically that's been argued to suggest that MOND might be a signature of quantum gravity effects coming in at very low accelerations. So kind of like how you need quantum mechanics to model a gas at very low temperature. So there have been some suggestions along that. Now regarding the interpolation function, as it's called in MOND, yeah, in general you'd expect the, well, for this, I guess just focus on the dotted black line. The solid blue line is the Newtonian sort of inverse square law, and this dotted black line is kind of what the gravity law would look like in MOND. And this is the MOND radius, and this is like A0 of gravity. So what actual physical length this corresponds to will depend on the mass. Yeah.
Any more questions, comments?
So what, have I understood right that MOND is suggesting a modification of Newtonian gravity in one direction,
Yes.
and Einstein has shown a modification to Newtonian gravity in the opposite direction? Is that more or less right?
Roughly. I mean, Einstein's theory is like modify Newtonian gravity like in regions where the velocities are very high.
Yes.
So near like a black hole. And MOND modifies it when the accelerations are low. One could ask like whether these two things occur sort of simultaneously, that the escape speed is high but also the accelerations are very low. This never happens in the real world because you would need a cosmologically large black hole to do that. Yeah, in general they don't address the same sort of system, but the in general, like we typically deal with systems which are not relativistic, and therefore general relativity would just reduce to Newtonian mechanics. So the extra corrections introduced by Einstein wouldn't be relevant. There are some relativistic tests of MOND as well, right? There are fully fledged relativistic MOND theories, which include both Einstein's insights about spacetime and MOND behavior in galaxies. There are theories like that as well. Typically, one doesn't need them, but you do sometimes do.
Okay. And the sterile neutrinos.
Yes.
I didn't catch that. I think near the beginning you said that dark matter would be mostly sterile neutrinos.
Yes.
And did you say that there's some evidence
On the
of their existence?
Yes, there is actually. There have been, I haven't shown that in a figure here, but basically there were hints found in various reviews, various publications from many different experiments.
Oh, okay.
Like one of the most compelling was these recent papers by Barinov from the Baksan experiment on sterile neutrinos. So that's like the best one. That's the acronym. But basically what it found is the flux of neutrinos was 3/4 what they were expecting, which is perhaps a hint that as well as the 3 ordinary neutrinos, you had a 4th type of neutrino that they weren't able to detect.
When I first read about dark matter, I really thought the physicists had lost the plot, you know, but it sounds as if that's...
We're still not sure that they haven't.
No, I agree. But certainly, just by changing the gravity law to MOND, you would still need some kind of dark matter on large scales.
But if you're finding evidence for the
Right.
existence of the sterile neutrinos, I can start to think it all makes more sense.
It does. From a particle physics perspective, it does. Because the kind of WIMPs, as they call it, weakly interacting massive particles people invent in the standard cosmology, would imply a much more major extension to the standard model of particle physics, which we know works extremely well at the Large Hadron Collider. You'd need to invent a whole new supersymmetric sector. And the most problematic aspect of this is that you would have super partners to the neutrinos. The ordinary neutrinos have masses of much below 1 electron volt. So the lightest supersymmetric part would have to have a mass above 10 trillion electron volts to be consistent with the LHC's results of not having found one. And this kind of asymmetry is extremely unnatural. Now a 4th neutrino or a sterile neutrino does not require any supersymmetry. It does require a minor extension to the standard model of particle physics, but this is actually good because we don't know where the neutrinos get the mass from, and a 4th neutrino would actually provide a fairly natural explanation through what's called the seesaw mechanism. So it would be hypothetical still, but much less so than the usual kind of cold dark matter.
So you say that the sterile neutrinos are obviously more massive than
The ordinary ones. Slightly, yeah.
What other property differences are there?
Well, the main one is that they wouldn't interact with normal matter at all, but they would interact with other neutrinos, and because neutrinos interact with mass, there is an indirect way to kind of do experiments that probe the sterile neutrinos. Like I was saying, if you were supposed to get some neutrinos and you only got 3/4 as many, that would be a sign about the sterile neutrinos. But yeah, they don't directly interact with sort of baryons, well, only through gravity.
Just a slightly aside thing, but do neutrinos not get their mass from the Higgs field like quarks?
Well, but according to such logic, they would have had the mass of 0. The masses of the ordinary neutrinos are not fully understood in the standard model.
Yeah, but doesn't it come from the Higgs field?
It's not fully explained that way.
No.
I mean, everyone was expecting the neutrinos to be massless, right?
Yeah, originally, yeah.
Yeah, but that's when they also they knew about the Higgs mechanism back then, right? So.
Well, it was postulated, yeah.
Yeah. But knew about the Higgs mechanism, they suspected it would give mass to all the ordinary particles. Even then it was thought that the neutrinos should be massless. It came as a big surprise that they have a small mass. And the reason for that is still not completely known. For the other particles, yes, it comes from the Higgs. Massive particles.
Well, in that case, we can only thank you for guiding us through this. Thank you ever so much. We wish you very much the best, because there's clearly a lot of work still to come here. So very, very, very good of you to take time to come and speak to us tonight.
Thank you.
Thank you.